Hello everyone, welcome back to our lectures today. Today we will be talking about amides, nomenclature and properties. So we're going to basically be covering both the nomenclature, physical and chemical properties of amides in this single lecture. And this is actually the last part of organic chemistry before we now resume and start talking about the biochemistry part of this class. Let's take it off from there immediately. I have a quote here. The quote is a health science quote from a renowned medical doctor, Dr. Jerome Adams. Dr. Jerome Michael Adams is the current Surgeon General. He's the 20th Surgeon General of the United States, and Dr. Jerome is an American anesthesiologist, former professor, and a vice admiral in the U.S. Public Health Service Commission Corps. And like I said, he was appointed the 20th Surgeon General of the United States by President Trump. He also formerly served as the health commissioner in the state of Indiana between 2014 and 2017. And he also had a short stint as a professor in a college. Now, this quote stemmed from his current war on the opioid crisis in the United States. He says, 10% of health is due to healthcare, 20% of health is genetics, and the rest is a combination of behavior and environment. And in fact, he was having a chat with another doctor, Dr. Anderson, talking about the current opioid crisis and how the opioid crisis is being managed, because he has actually been a strong advocate of the opioid pandemic and how to check that, particularly in the young individuals. So again, being a minoritized individual that rose to such a position, he remains a source of inspiration for the rest of us. Now let's immediately start our lecture. Learning objectives. We have 4 learning objectives to cover in this class. Like I said, this is just a one-stop lecture for amides. We're going to be covering everything about amides. And the reason why is because part of how amides are formed have been covered in the part of how amides are formed has been covered in the previous lecture regarding amines. And we're going to see how amines and amides are related. So we're going to classify amide as primary, secondary, or tertiary amides. That's the first one. We use IUPAC and the common names as well to name amide. And then we describe and demonstrate the effects of hydrogen bonding on the physical properties of amide. And finally, we write the equations for just the hydrolysis reaction of amide. We're going to be covering only one reaction of amide. And this reaction has an important biological connotation as we move on. Let's immediately take it off from there. Now, amides are those compounds that have the amide functional group. We call them the amides. So the functional group of an amide is a combination of the carbon and the nitrogen. See, the carbon is connected to a nitrogen, and that's what we say is an amide. So this is the carbon, and this is the nitrogen. So this is an amide combined together. Now, like I said, it has an amine portion. Oh, that's not what I wanted. It has an amine portion. The amine portion is coming from the amine. That's what we mean. Now, this nitrogen portion comes from an amine. And then it has the carboxylic acid portion. That side that is contributed by carboxylic acid. So this part comes from carboxylic acid. What you just removed from the carboxylic acid is the OH, whereas the nitrogen here comes from amine. So the combination of these two, the combination of those two is what gives us the amide functional group. And any compound that has this functional group is known as amide. And we're going to see that. Okay, immediately let's go to the next. Let's classify amides. Amides, just like amides, can be classified as either primary, secondary, or tertiary amines. And it depends, again, on the number of hydrogen that is attached or the number of arrow groups that is attached on the nitrogen. So the primary amines, let's see, the primary amines, of course, you have the carbonic carbon attached to nitrogen. The primary amines have 2 hydrogens attached to this. That means they do not have any arrow group attached there. They're just attached to the nitrogen that is attached to the carbonic carbon just have 2 hydrogens attached to it. So that here we call it a primary amine. And a good example is this one we have here. So this one is what? Ethanamide, or this is ethanamide or acetamide. So, and ethanamide is because it comes from now the carbonic carbon, usually the carbon number 1, this is 2. So this is ethane 2, and you put amide. That's how you name this guy. So ethanamide, and the old name is acetamide. Now, for the secondary amide, let's see. The secondary amide, one of those hydrogen has been replaced by an arrow group. So the secondary amide has either one arrow group or it does have what? One hydrogen. One hydrogen group. So a very good example is what we have here. So this is a methyl group that is attached to replace one of those hydrogen. So here, if we want to name this, we're going to name it, since it's attached to this nitrogen, it's going to be N. So this is going to be N-methyl ethanamide. This is 1, 2. N-methyl. So N-methyl ethanamide is what? A secondary amine. It's a secondary amide. And then we get to this one. Tertiary amide. In tertiary amide, they don't have any hydrogen because both of those hydrogen have been replaced by arrow groups. So you find out in our example here, we have, of course, this is the long chain, which is ethanamide. But here, what happens? You have an N group here, so an arrow group here and arrow group here, both of them connected to the N. So here it's going to be NN, 2 of them at N, NN dimethyl ethanamide. So NN dimethyl ethanamide, or the old name, NN dimethyl acetamide, is what? Is a tertiary amide. This is a primary amide. So these are the 3 classes of amides that we'll be looking at. And then we now go to their nomenclature. Now, I'm not going to be putting up enough rules about the nomenclature because at this time of this class, we've named a lot of compounds. And by now, we're almost getting used to naming almost everything possible at the level of this class. Now, but just to let you know, both of the nomenclature comes from particularly the carboxylic acid. Remember, the carboxylic acid. And then you're going to put an amide. So let's see what the name looks like. It says, use the carboxylic acid name. That's what I said. So it is meant from carboxylic acid and an amine. So the name will come from the carboxylic acid. So what happens? You're going to be dropping the IC. If it is in the old nomenclature, the IC will be dropped. The IC ending for the common name or the old name, for the common or the old name will be dropped. Or the OIC ending in the IUPAC name will be dropped. And then in each of these, either in the old name, remember if you have okay, let's come. If I have ethanoic acid, now I'm going to be dropping the acid, sure, and then I'm going to be dropping, this is the OIC. So if I drop this, I'm not going to put amide. So I'm going to have, if you do that, what are you going to have? Let's see. You're going to have ethane and you're going to have amide. And just like I showed you earlier, this is how we got this ethanamide, because it's derived from ethanoic acid. So that is exactly how you name this. Now, of course, for IUPAC nomenclature, in always the cases, the carbonic carbon is carbon number 1. It's carbon number 1. Now, the substituent or the attachment are now numbered and alphabetized. If there are other attachments to it, you have to do what? Number them and alphabetize them. Like I said, the number 1 carbon, which is the carbonic carbon, has to get the lowest number. Let's look at these examples that I've named already. In a few of these examples that I have already named, let's try to see what is going on. Now, each of them at the first row, I have the common name and then the IUPAC name down. So this is, okay, wait, let me see. So this is the common name, this is the common name, and this is the IUPAC name. That's what I have here. Now, this is formic acid. Formic acid, okay, now, it's not formic acid, it's formamide. But formic acid is derived, formamide is derived from formic acid. So the acid here is formic acid. So to name it from formic acid, what do you do? Remember what the name said? We're going to drop the IC. This is IC ending this. So what we're going to do is to drop the IC. And when you drop the IC, what do? You now put amide. So this will be formamide. That's how you come this name. So you drop IC and put amide. Then, if you want to name it from the scientific name, from the IUPAC name, of course, the acid here is metanoic acid. Metanoic, because it only has one carbon. This is, wait, let me write that well. Metanoic acid. In metanoic acid, of course, you're going to drop acid, that is sure. Then, what else? You're going to drop the OIC. So it's going to become methane. Methane. So what are you going to do? You now take the amide and join to it to become what? Methane amide. So that is how you name them. That's exactly what you do in the rest of them. So to name this one again, we count this is 1. This is only 1 carbon. So this one is now 1, 2. What it means is that this is from ethanoic acid. And if you remove OIC, it's going to become ethanamide to be the IUPAC name. Whereas acetic acid, just remove IC to become acetamide. The same thing here. This is, here the old name and the scientific name and the IUPAC name is the same thing. The common name and the IUPAC name is exactly the same thing. So from benzoic acid, we're going to remove OIC and throw away the acid to become benzamide. So this is benzamide and benzamide because this is made from benzoic acid. Like I told you, if you remove this and put OH, it becomes benzoic acid. But the moment you connect this here, it becomes benzamide. And let us take some examples here to see how this goes. Now, okay, just a last note before we take some reflection example questions. If it's still on nomenclature. Now, if an alkyl group, I already said this by the time I classify them, but this is important I make this note. If an alkyl group is attached to the nitrogen atom of the amide, so we're going to name the alkyl group. The name of the alkyl group precedes the name of the amide. What it means is that the alkyl group is going to come before the name of the amide, of course, like any other attachment. However, an italics N is used to denote that alkyl groups is connected or bonded to the nitrogen. Let's see some examples here. This is 1, 2, the longest chain in the IUPAC name. And of course, this methyl group is attached here. So we're going to say N-methyl acetamide and the old name, or M-methyl ethanamide, because this is 2 in the IUPAC name. The same thing goes there. Let's do this one. If you look at this one, this has an attachment here, and then there's an attachment here. The attachment here is metal, here is nitro. M and N, which one comes first? M comes first. And what's the length of this chain? 1, 2, 3, 4, 5. I already counted it. So if you count it, it comes from pentanoic acid. What it means is that in IUPAC, it's going to be pentane amide. So look at it, it's going to be pentane amide. Now, let's name the what? The attachment. Where are the attachment? M comes first and is connected to nitrogen. So we're going to say N-methyl 3-nitropentane amide. N-methyl 3-nitropentane amide. That is how you name this. And immediately let's go to the nomenclature reflection questions. The question says, name the following amide. Now we start by naming this amide. What's the first thing we do? We're going to start doing what? We're going to start counting our longest chain. This is the carbonic carbon, so we're going to give it number 1, of course. This is 2, 3, and 4. If you've done that, what it means is that this doesn't have any attachment both on the nitrogen and on this part. So it's easy for us to name, no attachment. And the longest chain is butane, so we're going to say butane. Then butane, of course, you're removing your OIC, it would have been butanoic acid. You're removing the OIC to become butane amide. And that is how you name this. Now let's go to this one. If you go to this one now, again, let's count. This is carbon number 1. This is 2, 3, 4. If you also count 1, 2, 3, 4. So what it means is that this is an attachment. This attachment is metal. And then there's an attachment again. There's another metal at this point. This is metal again on the nitrogen. So now, whenever you have an attachment on a nitrogen and on a carbon, remember, you're going to put the alphabet first. So we're going to say N, comma, they are the same thing. So it's going to be comma because they're identical. N, comma, in carbon number 3, we have another attachment, N, comma, 3. Since they're identical, you're going to use dimethyl. The longest chain is 1, 2, 3, 4. Is butane amide. That is how you name this. We now go to C. In C again, we count. This is the longest chain here. Looks like long one. 1, 2, 3, 4, 5. If you still count here, 1, 2, 3, 4, 5. So what it means, this should be an attachment. And this is metal, of course. This is an attachment. This is bromo. And this is an attachment. This is ethyl. If you put everything together, which one comes first? Bromo is B, comes first. And it's located in N. So we're going to say N, bromo. Which one comes next? E and M. E comes first. So it's going to be N. And ethyl group is located in N. N-ethyl. Then, methyl group is located in carbon number 4. 4-methyl. And then what's the longest chain? 1, 2, 3, 4, 5. Pentanum. It's going to be pentane. So it's going to be, okay, I'm going to put it here. We won't have enough spaces. It's going to be pentane amide. That is how you name that guy. And then we do the last one in this page, but not the least on this page. Now, there's an attachment here, 2, and there's an attachment here. Let's count the longest chain first, the first thing first. This is 1, this is 2, 3, 4, 5. If this is 5, what it means is that this metal is an attachment. But we have an attachment here. This is what? 1, 2, 3. This is isopropyl. Remember that. You remember? This is isopropyl. And then, of course, this is what? Ethyl. So if you put all of them together, which one comes first? E comes first. And it's located in nitrogen. So we're going to say N. Okay, I hope I'm going to have enough space. Let me push a little bit back. N. Ethyl. After N-ethyl, which one comes first? I and M. I comes first. It's going to be, and it's located in N. It's going to be N. Iso. Oh no, I don't like how that S came out. Isopropyl. N-ethyl, N-isopropyl. This is I. Of course, remember. N-isopropyl. Then, methyl group is located in 4-methyl. 4-methyl pentane amide. Now, remember, this is 1, 2, 3, 4, 5. The longest chain is 5. So we're going to be having 4-methyl pentane amide. This is not going to enter. I'm going to put it down here. I hope I'll have some space to do that. It's going to be pentane amide. Oh, I did do it. Good. Pentane amide. N-ethyl, N-isopropyl, 4-methyl pentane amide. That is how you name that particular one. Now, we now start talking about the physical properties of amides. Now, formamide or methanamide, which is the simplest one, the one with only one carbon, is the only amide that is actually liquid at room temperature. All other premier amides are solids at room temperature. Now, complex hydrogen bonding is possible between primary amides. Primary amides have can undergo extensive hydrogen bonding because of what? Remember again, because primary amide have two hydrogens attached to this nitrogen. And that makes them to have high boiling and melting point than, okay, let me put boiling too, boiling and melting point than the secondary and the tertiary amide. Please, this is amide. I just saw that now. Amide of similar molecular weight. Yes. Of course. Okay. So, we'll now look at this structure to illustrate that. This structure illustrates this for me. Please try to make this correction here. So, this is amide. Yeah, you just put D there. That corrects everything. Now, again, like I said, if we look at this now, this is a primary amide because this nitrogen has two hydrogens. Now, this is another primary amide, has two hydrogens. And you see, it can hydrogen bond from this nitrogen, from this hydrogen, and from this hydrogen. So it can form extensive hydrogen bond in three different places with another amide. So this extensive hydrogen bonding makes it to have high boiling and melting point than both the secondary and the primary amides. And we saw this trend when we also talked about the amines as well. Of course, this is the dotted line here, which is pink, is hydrogen bonding. This is another hydrogen bonding between. So these are intermolecular hydrogen bonding that influences this behavior of the boiling and melting point of primary amides. Now, continuing. Now, amide with fewer than 6 carbon atoms are soluble in water. Remember, because amides have this hydrogen that is attached to this nitrogen, it behoves that they can do what? They can hydrogen bond with water. Now, but what will decide how much they're going to hydrogen bond will also be, again, the length of the carbon chain. So amides that are fewer than 6 carbon atoms are soluble in water. Of course, all classes of amide will form hydrogen bonds with water because of the presence of both the carbonic carbon, of course, and the amino nitrogen. Now see, hydrogen bonding can also form between this is the carbonic carbon. It can form hydrogen bond with water here. So particularly if you see a primary amine hydrogen bonding, demonstrating the primary amide hydrogen bonding like I'm showing you here, you see that it has so many options to hydrogen bond with water. Look at what is going on here. Now, the water can hydrogen bond from this side, from oxygen. Remember, this is partial negative, this is partial positive. It can hydrogen bond from this central nitrogen here. This is negative, this is positive. It can also hydrogen bond from this hydrogen, can hydrogen bond to this oxygen of water, positive, this is negative. And then this one too can do the same thing. This is partial positive, and this will be partial negative. So it has 4 options of hydrogen bonding with water. And what this means is that primary amides will be much more soluble in water than the secondary and the tertiary amides. Like I said again, let me read what I have. I said primary amides form extensive hydrogen bonding because of the extra hydrogen on the nitrogen they have. So if you want to do the trend, of course, their solubility will be, the lowest is going to be the tertiary, will be lower than the secondary amine, and the secondary amine will be less than the primary amine. So the primary amine is going to be much more soluble because of that extra hydrogen on the nitrogen, making it to form extensive hydrogen bonding with water. Okay, immediately let's go to our reflection question. Some illustration here. It says, using dotted lines or broken lines, demonstrate hydrogen bonding between the following molecules. You say, you can use, this should be, you can use, I don't know why, so this should be, you can use more than one molecule of each. You can use more than one molecule of each, please. I'm sorry for that. You can make those corrections yourself. Now, so what are we going to, I'm going to redraw this guy. So redrawing this is, so I'm going to have this here. And then I'm going to open this up, hydrogen and hydrogen. Now, there will be hydrogen bond at this point. So let me put that first. A hydrogen bond can happen from here to the hydrogen of water. So I'm going to put water here. Then another one can happen from here. Of course, you know that this can happen from here. So this is oxygen is going to hydrogen. This hydrogen will go to oxygen. Remember that. So it's going to go to oxygen. And then the same thing will happen here. If I put another hydrogen. Okay, now I'm going to use the red to draw the main molecule. So this is going to be. And then there's another hydrogen bonding too. Now there could be there's also a hydrogen bonding prospect from this nitrogen. We'll go to what? A hydrogen. Of course, you're going to have a hydrogen here. Giving it 4 options, 4 molecules of water surrounding this and forming extensive hydrogen bonding. So of course, all these blue lines, the blue lines are, remember the blue lines are hydrogen bonds. Do not forget that. These are hydrogen bonds. So here oxygen to hydrogen, here hydrogen to oxygen, here nitrogen to hydrogen, here hydrogen to oxygen. So this is how you do this problem. Like I always say, always feel free to pause the videos, try out the problems yourself, and always come back to check for comprehension. All right. Now, what about the reactions of amide? I told you for the reactions of amide, we're going to be focusing only on one of them. We're not going to be going a lot deep into many of them. Now, of course, it's important I say this. Amides are neither acidic or basic. Why? What's the reason? Now, look at the reason. The carbonyl hydrogen, the carbonyl group that is bonded to the nitrogen, the carbonyl group that is bonded to the nitrogen destroys its basicity of the amine. Remember, it comes from an amine, but the moment the amine combines with the carbonyl carbon, it destroys the basicity of the amine. Now, what about the acidity? Now, look at what happens to the acidity. The nitrogen of the amine replaces the acidic OH group of the carboxylic acid. So it's a kind of a neutral compound because the combination of those two functional groups have destroyed the acidity from the amine and the acidity from the carboxylic acid and the basicity from the amine. So we can indirectly infer that they are neutral compound because they are neither acidic or basic. Now, the only reaction we'll be considering in this case will be hydrolysis. Hydrolysis is the reverse. Remember the reaction we talked about when we did amines is the reverse of amidation, breaking it down with water molecule. So amide is cleaved to produce carboxylic acid and an amine in hydrolysis reaction. Like I said, which is the reverse or opposite of amidation reaction. Now, if you look at it, what is happening here is that water comes in as a machete to cut this. And when this is cut, remember, water is always H and OH. The OH comes and connects to this to form carboxylic acid here, whereas the hydrogen now goes to connect to this guy here to form the amine. So amide hydrolysis results to the production of carboxylic acid and amine. And of course, this is very common in what? In the body particularly. This can be done either by an acid, a base, or an enzyme. But much more importantly, as it relates to this class that is a health science class, enzymes do this particularly when they begin to digest proteins. Proteins are polypeptides. So they have this amide or peptide bonds, which the enzymes, which the protein and the protease enzyme goes there to cleave those peptide bonds to release, of course, to break them down into amino acids. Let's now take some reflection questions to drive home this very important point. Now, again, this is reflection 2 here. We're going to be doing the machete, cutting this place with water. If you do that, you're going to have your, of course, your H3 will remain. You're going to have this connected to this. Now, if you cut out this, remember this is H and OH. The OH will come and join here to form this acid. Of course, this is ethanoic acid or acetic acid plus. Remember, this side now is going to take the hydrogen. Of course, so what it means is that if I put this, the NH you have there now. So if you add another H to it, it becomes H2, and then you're going to connect this one here. The H2 is there. You connect this here. The H2 is there. You connect this one. So of course this is 1, 2, 3. So you see this is now 1 propane. Actually this is 1 propane amine. That's exactly what we have here. This is ethanoic acid. Ethanoic or acetic acid. And of course, if you want to name this one, of course, we are talking of amide. This is 1, 2, 3. This is 1, 2, 3. This is propyl connected to this. The longest chain is 1, 2. This is a amide. So this is going to be N propyl. No, I'm not going to put hyphen. You don't need it. 1, 2. This is a 10. You now put amide. Exactly. So that is that. Well, you don't need to remember when I'm doing my nomenclature, as usual, if you've been listening to my lectures, you don't need to name it. But I do these things just to give you a broad spectrum of what you're going to learn from me. To do this one again, I'm not going to name this one. I'm just going to break it apart. If you break it from here as usual and add your OH, you're going to have this. That's what you're going to have. And then, of course, you're adding the OH here, 1, 2, 3, to have this. Plus, you're going to have this. Remember, you're going to have this. Then it's 1 hydrogen before. If you add another hydrogen, it's going to be this. So this is what you're going to have. You do not need to name them. All right. We now go to the next reflection question. Now, the next reflection question now becomes the direct application of amide hydrolysis in biological system. I gave you this kind of problem when we also talked about formation of amides from 2 amino acids. Now, I have a dipeptide which is made up of 2 amino acids. This is a dipeptide. This is a dipeptide. And this dipeptide, of course, that's fine. This is a dipeptide. And this dipeptide is made up of, if you look at from this part, from here to here, is made up, is the cysteine. So this is cysteine. Here now is serine. From here, this point, from the nitrogen to this point is serine. So we're going to call this cysteine serine. Now, which is a dipeptide, 2 amino acids combined together. So now, water molecule is going to come. Usually what happens with enzymes in the body, they're going to use water molecule and come and cut it at this point. And when you cut it at this point, you're going to have 2 amino acids. So look at what you're having. You're going to have this. Hydrogen is attached here. You're going to have this H here. Then you have this. And then, remember, the OH group from water. Remember the OH group from water here is going to come and connect here to form cysteine. This is cysteine plus, since I'm not going to have enough space there, so I'm going to just write the cysteine there. So this is cysteine, amino acid, plus this one will now be, remember, what will happen to this one? Now, remember, this is the amide bond that we're cutting. This is the amide bond, so we're cutting it from here. And then you're going to have this one. Remember, this one starts from the N here. This N, of course, will accept another hydrogen to be 2. And then you have this one here. You have this guy here. You have this and this. Of course, this is the serine. So in a dipeptide, this end, of course, this end is actually what we call the C-terminal end. This is, because the end with the C, this is the C-terminal end. We're going to see this in protein. And then this will be the N-terminal, because it ends with amino acid. That's exactly what this means. But we're going to get to these ones. But what I just want to let you understand here is that a dipeptide, or most peptides and polypeptides, form peptide or amide bond. And when you break it through hydrolysis, you release the constituent amino acid that make them up. And then we now go to the last but not the least of what we're doing today, which is still the same type of example I had there. Look at what happens again. In this case, this is 2 amino acid now. In fact, this amino acid here, this is another dipeptide. This is actually a glycine. Glycine is the simplest amino acid. Glycine is the simplest amino acid. And then this is the second to the simplest amino acid, alanine. So this is a dipeptide again. I'm going to chop them up from here. If I do that, I'm going to have N. I'm just going to put H2 here. just to reduce my space. And then this is going to be hydrogen, this is going to be hydrogen. And then this is going to be this guy. Remember, the moment you chop it here, you're putting an OH here, plus this is now glycine. So this is glycine proper, because here it is glycine that makes it. So this is glycine plus. Remember, this is just made from glycine plus this. So this is not like it is the main glycine. Just know that. But just to tell you that this is made up from these two amino acids. It's important you get that clearly. So this is proper glycine amino acid. So glycine, then what about this one? Remember, this one has one H here. It's going to accept the H from water, and then we're going to complete the rest. So you're going to have this, and then this will be connected to this methyl group, and then this is going to be this. Every amino acid, remember, every amino acid must have the carboxylic acid end and the amino end, because that's why we call them amino acid. It has two functional groups that are attached to this carbon. This carbon actually is what we call the alpha carbon in amino acid. But we're going to get into those details much later in this class. Now, I brought out something just to conclude the class. I brought out something that we did in the previous class, which is the opposite of this reaction. Remember, the opposite of this reaction is amidation, whereby you form amide. And I gave you some example whereby I joined two amino acids. That's what I'm doing here now. I'm going to be joining serine and tyrosine. Tyrosine is an aromatic amino acid. It's an aromatic amino acid. And remember, it has a phenol. This, if you remove this now, this is a phenol group. The difference between this guy and this guy is that you will take this side and attach to this. It becomes that. But that is not what we're doing now. By the time we talk about proteins, we're going to get this even much better. So if we join these two together, we're going to be joining. Look at what we're doing here. This one is going to lose this. This one is going to lose one of the hydrogen, and we join them off from here. Every other thing will remain the same. So to conclude this particular lecture, I'm going to be doing that just again as a brain teaser. This is what we did in the last lecture. So you're going to have this one constant. You're going to have this CH2 here. So now I'm going to have, of course, this amino group here is not going to be touched. The one at the end is not touched. But this one, it has O here. This one is going to be touched. Now this N will come and join this one here, losing the OH group, and then it will lose also one hydrogen. So one hydrogen will remain, and then we're going to connect the rest of this to this one. So this one will now be connected to this, and then you're going to have this and this. So this, of course, again, remember, this is the amide bond. This is, of course, remember, this is C. This is C here. Oh, that C didn't come out well. This is C. So it is this amide bond that when you break it again in the reverse reaction, you produce serine and tyrosine. So of course, if you want to name this dipeptide, you're going to call it tyrosyl serine. Is, of course, a dipeptide. A dipeptide. That's exactly what we've done at this point. And having said that, we've come to a successful end to the organic chemistry part of this lecture. The next thing we're going to be going into will be the biochemistry part. Once again, thank you for listening at this point. Bye.